Every branch of mathematics has some notion of sameness. The idea being that as far as that subject is concerned, these two objects, even if they might be different sets or they might lie in different places, are treated the same. They have the same properties under whatever mathematical structure we're looking at. In geometry, this notion of sameness is called congruence. And we're going to talk about segments being congruent, angles being congruent, triangles being congruent, and so forth. But we need to start with segments. And the congruence of other objects is going to have to wait a little bit later until we develop some more structure in terms of how do we measure things like angles. Segments, however, we have a natural way of measuring, because when we look at a segment is a subset of a line, and it's got two endpoints, A and B. And so we can associate a measure to this. The most natural way of doing that is to look at the distance between A and B. We're assuming that all of the geometries we're looking at are metric geometries, meaning that there is a distance between any 2 points that satisfies the various distance axioms. So we are intuitively going to think of congruence of two segments. Let's say that we want to say that AB is congruent to segment CD over here. And we're going to basically say that's true if we can take one of our segments and move it, rotate it, translate it so that it lies right on top of the other one, exactly on top. Now, this intuitive process of moving things around so that they lie on top of one another is difficult to make precise in terms of the geometry that we've had so far. However, we can do something else. We can associate a length to each segment in our geometry and simply say that two segments are congruent if they have the same length. In fact, that's exactly what we're going to do. So, definition 17. We say that the segment AB is congruent to the segment CD if the length AB is equal to the length CD, and we write, in this case, that the segment AB is congruent to the segment CD. Now, some important points of notation here. Notice that these two statements look similar, but they've got some differences, and those differences are important. So remember that when we just write AB without any decoration on it, that means the distance from A to B. So that's the distance from A to B. This is the distance from C to D. In particular, if I just write down AB with no additional decoration, that's a number. And so the statement AB equals CD means that the number AB is equal to the number CD. And here we're just using equality of real numbers, which we're familiar with. On the other hand, the segment AB is congruent to the segment CD, which we have in the second part of the sentence, uses different notation because it's comparing different things. So AB with a bar over it is not a number anymore, it's a set of points. It's the segment that lies on the line containing A and B, and it's the set of all points that lie between A and B and A and B together. So this is the we're now saying that we're comparing two segments to each other, which means that we're comparing two sets of points. Now, the difference between these two statements, or these three statements, should be I want to make very clear. So, on the one hand, we have that segment AB is congruent to segment CD. We have that AB, the distance from A to B, is equal to the distance from C to D. And then we have that the segment from A to B is equal to the segment from C to D. So, the first two terms here mean exactly the same thing. By definition, two segments are congruent if the distances between the endpoints of those segments are the same. And so AB is congruent to CD if the distance from A to B is the distance from C to D, or in other words, if the two segments have the same length. However, that doesn't mean that the segment AB and the segment CD have to be equal. This symbol right here, this equality, now means equality of sets, whereas the equality in the second case is equality of numbers. So to say that the segment AB is equal to the segment CD means that they contain exactly the same points. And we actually looked at this a little earlier when we looked at segments in the first place, and two segments are equal if and only if the set of vertices AB is the same as the set of vertices CD. If A equals C and B equals D, or A equals D and B equals C. So equality of segments is a very, very strong condition. So for instance, the segments that are at the top of the page are not equal, but they are congruent. So what we can say is that if two segments are equal, then they're certainly congruent to each other, because if the set AB, the segment AB, which is a set, is equal as a set to the segment CD, then the lengths of those two segments are definitely the same, but it doesn't go the other direction. You can have two segments that are congruent without actually being equal to each other, which is very much the whole point, actually. In most branches of mathematics, as I said, we have this notion of sameness, and usually equality is too restrictive a notion of sameness. We want to say that these two things behave the same way from a geometric point of view, or an algebraic point of view, or a topological point of view. And certainly if two things are exactly equal, that'll be true, but there's often a lot more than that. So I want to make it very clear that these are three very different statements. Now the first two are equivalent to one another, but the last one isn't. And part of the danger here is that, you know, it's the same notation being used in both cases. So we use the segment notation in two of these statements. We use equality in two of these statements, but you need to be very, very careful about how you're connecting them up to one another. The big takeaway here, equality of segments is almost never relevant for us. This third condition over here. This is almost never something that we're going to be proving exactly. We're almost always going to be proving that two segments are congruent, not that the two segments are equal. So let's see some consequences of this. The definition allows us to prove certain things very easily about congruence of segments. Things are going to get a little more complex when we move into congruence of angles and triangles, but segments are actually fairly straightforward. The first thing we want to check is Theorem 18, or sometimes we can call it Theorem C1, the first theorem, the first congruence theorem, congruence for segments. And it says that congruence of segments is an equivalence relation. Now, an equivalence relation is a relation, a way of comparing two things that behaves in three essential ways like equality. So I'll go ahead and talk about those quickly as we go through the proof. So there are three things that a relation has to satisfy in order to be an equivalence relation. The first one is that it has to be reflexive. That is, I want to show that for all segments AB, we have that a segment is congruent to itself. So let's prove that. Let's let segment AB be a segment. Since the distance from A to B is equal to the distance from A to B, we have that the segment AB is congruent to the segment AB. So really what we've used here is we've used the fact that equality on real numbers is reflexive, because I know that the distance from A to B is a number, therefore it's equal to itself because equality is reflexive, and therefore we can take that back to say that, well, then that means that a segment is congruent to itself. So that's a reflexive, congruence of segments is a reflexive relation. Next we need a symmetric relation, which means for all segments AB and CD, if the segment AB is congruent to the segment CD, then the segment CD is congruent to the segment AB. In an equivalence relation, the order that you write things down in doesn't matter. Now, this is different from other relations like less than or equal to, where the order that you write things down in might matter. But we want to say that congruence doesn't matter. It should be the same thing to say that AB is congruent to CD and to say that CD is congruent to AB. So I'm going to start off by saying let AB and CD be segments, and suppose that the segment AB is congruent to the segment CD. Well then, that means that AB equals CD, because that's just the definition of what it means to be congruent as segments. And AB equals CD. So now we're going to use the symmetry of equality. So that means that CD is equal to AB. So CD is congruent to AB. You'll notice that for both reflexivity and symmetry, really we've just used the fact that the relation of equality is reflexive or symmetric, and then gone back up to the level of segments that way. That is pretty typical when you're defining a relation in terms of another relation that you already know is an equivalence relation. And the same sort of pattern is going to happen for the third condition we want, which is that we want the relation to be transitive, which says that for all AB, CD, and EF segments, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. So we want to show that if that we can essentially chain along congruences. If this segment is congruent to that one, which is congruent to that one, which is congruent to that one, which is congruent to the last one, then the first one and the last one are also congruent, that we can chain along a string of congruences like we can string along a chain of equalities. And in fact, that's exactly what we're going to do to show this. So we're going to suppose that segment AB is congruent to segment CD, and segment CD is congruent to segment EF. Then we have that AB is equal to CD, and CD is equal to EF. But now we know that equality of numbers is transitive. We know AB is equal to CD, CD is equal to EF, therefore AB has to equal EF. So therefore AB has to equal EF, and so that means that the segment AB has to be congruent to the segment EF. So we've showed that congruence of segments satisfies the conditions of being reflexive, symmetric, and transitive. And those are exactly what you need in order to be an equivalence relation. So in fact, at this point, we're done. So congruence of segments works like equality, but it's not equality. And so we need to make sure to use the right symbols and be very precise about what we mean. Because to say that two segments are equal and to say that they're congruent, there are two different things. The most important theorem that we have from this section is theorem 19. We can call it C2, or more commonly we'll refer to it as the segment construction theorem. And this theorem we are going to use all the time. We're going to use this very, very often as we move forward in the course. So, given a segment AB and a ray CD, there is a unique point E in the ray CD such that CE, the segment CE, is congruent to the segment AB. Before getting into the proof, let's see visually what this means. So let's say we've got a ray here, and this ray is the ray CD, so starting at C and passing through D. And then we have a segment over here. The segment goes from A to B. And what this is saying, what this theorem is saying, is that we can find some point over on the ray CD such that CE, the segment CE, is congruent to the segment AB. Or another way of thinking about it, there's some point over on the ray where the segment from C to that point E is a copy of AB. We're constructing a copy of the segment AB onto the ray CD, hence the name of the theorem, the segment construction theorem. Now, we can visually see how that happens. If we imagine taking a copy of this over here, and then literally lining it up like this, then we can see where we want to put E. We would want to put E right here. And if we do that, then the segment CE is going to be congruent to the segment AB. So that's the idea behind it. And so in particular, this means that we should be able to construct copies of any segment we like onto any ray that we like. And that's exactly what this theorem is saying. The proof is not too difficult, but a lot of that actually depends on the fact that we've spent a bit of time developing the ruler postulate, the ruler placement theorem, and so forth and so on. So we want to start off with the following. Let's let F be a coordinate system for the line CD such that f of c equals 0 and f of d is positive. The ruler placement theorem says that this can always happen. Note that in this case, we have that the ray CD is equal to the set of all points x in the line CD such that f of x is greater than or equal to 0. So we can tell whether a point on the line is in the ray CD by checking whether its coordinate is positive or negative. So now we want E to be a point on the ray such that the distance from C to E is the same as the distance from A to B. So we want the distance from C to E to be the number AB. But this distance is also determined by the coordinate of E. Now C has a coordinate of 0, which means that the distance from 0 out to E is just the coordinate of E, which means that we want E to be a point on the line which has a coordinate of AB, the number AB. We can do this efficiently in the following way. Let's let E be F inverse of AB. We know that F has an inverse because it's a bijection by the definition of a coordinate system. AB is a real number, and therefore there is some point on the line CD that has a coordinate of AB. And so we're going to call that point E. So there's two things that we need to check. We need to check that E belongs to the ray CD, and we also need to check that the segment CE is congruent to the segment AB. So let's do that here. So this means that f of E is equal to AB, and the distance from A to B is positive. The distance between any two distinct points are positive, and A and B being two endpoints of a segment means that they have to be different. So, in particular, this means that E belongs to the ray CD. And that's based on what we have in the last line. The ray CD is the set of all points on the line where the f of that point is non-negative. So also, we have that the distance from C to E is equal to the absolute value of the coordinate of C minus the coordinate of E. So the absolute value of f of C minus f of E. By construction, f of C is 0, and f of E is the distance AB. And when we take absolute values of all that, we get AB. So that means that the distance from C to E is equal to the distance from A to B. So that means that the segment CE is congruent to the segment AB. So that's great. We've found a point E on the ray such that the segment CE is congruent to the segment AB. Now we're not actually done. There's one little word in the theorem that's very, very important that we haven't proved yet, and that's unique. The theorem said that there was a unique point E that made this happen. What we've done is we've constructed a single E that makes this happen. But we need to show that there aren't any others. A lot of times proving uniqueness will look a little bit like our original construction, but that doesn't mean that we can skip it. Often, the best way to prove that something is unique in geometry is to assume that there's another one, basically. Give a new symbol to a point that satisfies the same conditions as the one we've constructed, and show that it actually has to be equal to the one that we constructed. That's how we can do this here. So we can say, let E prime be in the ray CD such that the segment CE is congruent to the segment AB. CE prime, rather, is congruent to the segment AB. So let's suppose that E prime is another point that satisfies all the conditions that we've required of E. But then that means that CE prime is equal to the distance from A to B. So that means that AB is equal to CE prime, which by definition is the difference of their coordinates. So that's the absolute value of f of c minus f of e prime. So f of c is 0 minus f of e prime. So that all just becomes the absolute value of f of e prime. But we know that f of e prime is non-negative because e prime belongs to the ray CD. So this equality here is because e prime belongs to the ray CD. Well, why does this finish it off? Because now we have that f of e prime equals AB, but we also know that f of e equals AB, and f is a bijection. So that means that e equals e prime, and so we're done. So if we had any other point on the ray that satisfied the same conditions that E does, it would have to be equal to E. And therefore, that shows that E is unique. It's the only point that does what it does. All right, there's one more theorem with 3 parts to it that comes up not quite as much, but occasionally. So first, we've got C3, which is called segment addition. These three, or the first 2 of these parts of the theorem deal with betweenness and congruence. So segment addition says that if B is between A and C, B prime is between A prime and C prime, AB is congruent to A prime B prime, and BC is congruent, segment BC is congruent to segment B prime C prime, then segment AC is congruent to segment A prime C prime. Now we can start sketching this out. We're going to start using figures to understand our arguments soon when we start dealing with more complex figures. So the situation is essentially this one. Here we have ABC, A prime, B prime, C prime, and what we've been told in the problem is that the segment from A to B is congruent to the segment from A prime to B prime, and we'll usually denote that using marks like the following. A line or two lines, or more if we need to, in the middle of a segment indicates that all the segments with the same number of tick marks in them are congruent to one another. So this problem is saying that if AB is congruent to A prime B prime, BC is congruent to B prime C prime, then in fact the whole segment AC is congruent to the whole segment A prime C prime. Beg pardon. This is an exercise, but let's look at a similar one. C4, segment subtraction. This is something similar. It has the same first setup. If B is between A and B, and B prime is between A prime and C prime, segment AB is congruent to segment A prime B prime, and segment AC is congruent to segment A prime C prime, then segment BC is congruent to segment B prime C prime. So this is doing something slightly different. So for this problem, we're saying that AB is congruent to A prime B prime, and then if I look at the whole segment AC, that's congruent to the whole segment A prime C prime, and if I do that, if I have that situation, then that means that my segments BC and B prime C prime have to be congruent also. So let's look at the proof of this very quickly before we make the last statement of the proof, of the theorem, rather. So the proof for this is pretty straightforward. We want to prove that BC, the segment BC, is congruent to the segment B prime C prime. We have one way of doing that at this point, and that's to prove that their lengths are the same. So let's start with BC here. Now BC is equal to AC minus AB, and that's just rearranging the equation that we get based on the betweenness relation. We know that this statement, B is between A and C, means that AB plus BC equals AC. So all I'm doing is I'm moving the AB part of that to the other side in order to get BC by itself. Well, now we've got a couple of things we can say. We know that the segment AC is congruent to the segment A prime C prime, which means, the only thing it means, is that these two numbers are the same. So this comes from the fact that segment AC is congruent to segment A prime C prime. And similarly, we have that segment AB is congruent to segment A prime B prime, which means that the length AB is equal to the length A prime B prime. So that's gotten us something involving just the prime terms. But now A prime C prime minus A prime B prime is B prime C prime. And this is since B prime is between A prime and C prime. So again, using the fact that A prime B prime plus B prime C prime equals A prime C prime, but just rearranging it. And that's basically all there is to the proof. The full proof will have some more, we'll have a conclusion to it and a little bit more words to help the reader along, but that's the idea behind it. All right, and the last one is the following. Given a segment AC, there is exactly one midpoint, i.e. a point B with B lying between A and C, and the segment AB congruent to the segment BC. So if I've got a segment, I can find the midpoint of it, and it's always unique. And the proof of this is actually kind of similar to the segment construction theorem before, where we're going to use a coordinate system. So if F is a coordinate system for the line AB, I'm sorry, line AC, what we can do is let B be the inverse of, well, the average actually of the coordinates of the two endpoints. So whatever the two endpoints are, they've got coordinates. Those coordinates are just numbers, and therefore those numbers have an average. There's a midpoint in the real number line. We can find that midpoint and then just say, all right, what point was it in the original line that got mapped to that point, that got mapped to f of A plus f of C all over 2? Whatever that was, that's your midpoint. Now, of course, there's some more work to do. Once you determine that this is B, you have to show that the segment AB is actually congruent to the segment BC. You have to show that it's unique, which follows something very similar to our proof for theorem 19. So these are our basic statements about congruence of segments. It turns out that segments are simple enough by themselves that we can understand them very, very well pretty quickly. It's once we start moving on to more complex figures involving angles and triangles and such that we're really going to see the power of a lot of these theorems that we've worked on today.